Hey, so it's been about a year now since I last did my last QLab lecture discussion thing. I did some additional work last year after I ran the second session, and I made some neat stuff, but I never presented it. So I'm sitting around bored on a Monday night, and I'm thinking, I should just get this out there because people seem to like this stuff, and it was pretty cool. So let's go back and see if I can remember what the heck I was doing. When last we spoke, I was looking at caves, right? I was generating these worm-like caves. Let's see if we've got some video of that. I was generating these worm-like caves. Yeah, here we go. By using cellular simulation. So these were veins. The cells are connected to their neighbors, but they repel other cells which aren't connected to them, which are not their neighbors. So you get these branching like patterns. And I think I talked a little bit about... Do I have a movie here? What do I have in here? I don't have much of anything in here. Let's see what the README says. README. Extend neighborhood bound for computing ISO service to get rid of creases. Okay, that's not interesting. Don't always write these. Oh, no. Oh, so Run 31 was an experiment I probably did. Well, there's the stalactite stuff. I know I did stalactite stuff. That was my ending discussion for the last video. But I don't see that video here anywhere, so, whatever. But to recap, I used a displacement shader to create just this jaggy surface on the surface of the cave system I generated. The point in bringing that up is that shortly thereafter I decided to explore sort of new ground with the cellular simulation, also using extensive use of shaders and displacement shaders, but not for these caves veiny stuff. If you recall from a long time ago, a year ago, when I first discussed the cellular stuff, I was talking about not only the circulatory system, the tubes, the veins in the tubes, and the whatever. I'm a really good drawer, can't you tell? And then these branched, and you saw them. I also mentioned skin, and I think I ran some tests. I won't go over that stuff too much. But what I talked about was if you get rid of this connectivity on the cells and you just pack them in on a 2D surface, you can create what I was referring to as skin-like patterns. So that's what I wanted to look at next. Now, what I would like to do is I showed here. It's just better if I go back and see if I can find, but it's going to be so long ago. I literally can't find it. I give up. Is that true? That's so horrible. Okay, let's hang on. No, that'll be too hard to find. Okay, so here's the veiny stuff I was talking about. Here's the stalactite stuff I was talking about. None of the pictures of the stuff I want to show you. There's veinies. Yeah, great. Open no match. Oh, do I just not have any TIFFs? Oh, I wasn't rendering to TIFFs, was I? I was rendering to JPEGs? Ah, yeah. I was. Cool. Okay, so yeah, here's what I'm talking about. So skin-like stuff where you can strain the cells to a two-dimensional surface, but then you give them rules for other parameters. Like obviously here they get bigger as you go to the right. Here I was doing veiny stuff but constraining it to a plane. Here this doesn't look like much, but it's actually kind of cool. Oh, here's veiny stuff confined to a sphere, and also kind of fat, you know, fat enough so that they're intersecting with each other. Here's kind of interesting. They're just equidistant. So these are evenly spaced spheres on a sphere, in case you need that. And this is kind of interesting too. In fact, this is very close to what I'm doing today, where in the center you get these big ones, and out towards the edges you get little ones. So, but putting them inside squares like that isn't terribly interesting, honestly. And it's kind of misleading when you constantly see these pictures like this inside a square. It makes you think, oh, well, you can't do anything more interesting or more realistic than, you know, confining these things to squares, which is great if you're trying to create patterns on squares, but, you know, wouldn't you rather create a pattern on the letter Q? Yes, of course you would. So, if you did want to confine those circles to the letter Q, how would you do it? Well, I don't know. I'll give you a second to think about it. I'll give you a hint. The input to this system I want to be an image, because I don't want it just to be the letter Q. I want it to be any image I give it, you know, any black and white image, so that, you know, whatever shape is in here, that's what the cells conform to. In the past we used stuff like springs, you know, we used repelling forces, springs to keep the veins, when we did the veins, right, which was just a sequence of these cells in a row, we simulated virtual springs between them to keep them close together. And then for you know, other veins, right, so that these veins wouldn't get too close together, there was a little repulsive force between non-connecting cells. So that's the kind of stuff we have. But how can we apply it to this texture map? Well, so if we want our cells to stay inside the Q, and we start off with just this one here, what are we going to do? Well, okay, I'll let you stop thinking about it, and I'll just give you the answer. We're going to, let me turn this Q on its side. What does that mean? Let me turn it on its side. So, looking at a slice of the Q, here is the left side of the circle, and here is the right side of the circle. And in that drawing, I had the cell in the middle. And what I wanted was for him to go into the Q. What I'm going to do is I'm going to blur that image and then use it as sort of, well, I'm going to use it as a gravity map. Okay? So in that case, this sphere is going to, I mean, he's right in the middle. But in general, the spheres are going to, I'm going to simulate some sort of gravitational force on them that pushes them down with respect to this map I've created. And I already sort of gave away the hint. I'm going to create this map just by blurring that image. Oops, my recording software crashed. Luckily it didn't take my recording with it. What was I talking about? Oh, I was talking about the letter Q, and I was talking about blurring it and then using that as sort of a gravity map, which is kind of hard to envision, I think. So I made a little visualization tool for it. But it's not in Run 31. It's in Run 32. So like before, these run files are going to be available on the interwebs. So what do we have? Okay. So q.pgm. So a PGM file. Can I just open it? q.pgm. No, it's coming up in Open Office. Yeah, great, fantastic. Oh, but Open Office is able to view it. Weird. PGM is this really primitive image format. Oh, maybe I was already using it in these discussions. Well, whatever. It's a very simple image format that I put my Q in. I think I did it with Photoshop. Yeah, so like I said, I did this a year ago, so I actually don't remember all this stuff. But, you know, whatever. Anyway, here's my visualization. Let's make it bigger, I guess. You can think of the Q map. Let's see, is there open Q-blur? Oh, is it going to open Office again? No. Just doesn't even know how to oh yeah, it is. Nice. Okay, so here, you know, obviously is the Q blurred. No big deal. But when you apply that, like we were discussing last time, as a displacement map, you can see how it distorts the surface of this checkerboard, and you can kind of see how this gravitation thing is going to work. It's the cells are going to fall into this, and it's going to keep them in shape. So that's how I get custom shapes with my cells. There is a problem doing it this way, though. The process of blurring causes the oh, here, let's look at this. I made it an animation. I may as well show it off, right? Oh, that's so nice. There's a problem in that blurring the Q loses detail. And I had to blur it pretty, you have to blur it quite a bit in order to catch all of the cells. And that means losing, like, there was nice, so it was a funky little font, what is it, Monaco or something? One of the old-time Mac fonts, that has this neat detail in the descender here that's completely lost with the blur. So what do we do about that? Well, we don't blur it. We create what is known as a signed distance function of the map. Compute signed distance field for well. What is that? A signed distance field is so for every pixel in the image, the value there is going to be an encoding of the distance, the shortest distance, I should say, the shortest distance to the inside of the Q. Because it's linear like that, it's just the distance to the inside of the Q. What we'll get now, if we look at the Q halfway, say this is the Q half. Remember when we blurred it, we got those nice round shapes. Now what we're going to get is, as you get away from the Q, the distance from the Q is going to increase linearly. Here's going to be the same thing, except right here, we're gonna it's going to be the minimum of these two, because it's the closest distance to the Q. I don't know if this is very clear. And then the other thing about it is this is signed, which means when you get inside the Q, it goes, the distance is negative. So this path, this thing continues. And okay, so let's look at what this well looks like. Pretty similar, but not as rounded. Not as pleasing to look at, but has has the details that were lost in the blurred version. So like, you know, you can see this, you can actually see the serif there. That little funky detail I was talking about is very sharp. And you're thinking, well, how do I compute these sign distance fields? Well, you just look at the code in sdf.cpp, which does the simplest thing you could possibly imagine, which is for every pixel in the image, search some neighborhood around that pixel, trying to find one that's white, and just record the distance to the nearest white pixel. And so here's some code for you to do that if you need to. I can't remember if I was reading images before. I can't remember what I was doing before. So you'll see Q image here. I don't think I was. So the Q in the Q cell library. Is it just cell.cpp? What did I call it? Yeah. So this is the cellular code that I showed you in all the other classes, right? But now we've got this Q image, which loads PGMs and saves PGMs, which are very basic files, like I said. Basically, you just loop over them and print out the values. The nice thing about them is that most software, you can use the PBM library to convert it to, you know, pretty much any other file format you want. So it's really easy to generate, and then you can turn it right around into other file formats. I think I do that in my make file here somewhere. Yeah. So PGMs are made from ping files. With this program, SDR. Oh, that's a shader file. Well, these are this is all crap. Okay, well, whatever. Forget about it. But it looks like I have some kind of movie here. We should check that out. How did I change simulate? Readme. I don't remember what. Well, let's just look at it. Cells.move. Yeah, great. So I forgot to remove the cells.move file. Let's just get rid of that right now. That's very annoying. So I have all these cell files from the simulation, but no output to show for it. That seems bogus. Seems bogus. Okay, well, whatever. Trying to make this play with size with respect to SDF, sign distance function. Yeah, I wish I had an animation from that last one. Well, here's an animation for this one. Oops. So I'm in run 34 now. And there's that stupid well movie again. Let's get rid of that. Let's clean this up. Okay. Open cells.move though. Here we go. Okay, so now we finally get a simulation where I think we get to finally start to see, yes. So here is the cells in, let me move that out of the way, the cells being simulated with that sign distance field to control their fall into the gravity well of the Q. And that's pretty cool. You know, I've seen cooler things, obviously, but this is, as far as generating, the idea here is to generate synthetic skin. This is a good basis, as they say. Maybe I should look at the code to do that a little bit. Well, so we've got well force and image well, And what does he do? Oh, and so he takes an image, takes a position, generates a new position, and it does that by calling image gradient. And image gradient, all that does is sample the image in a couple of places to determine the slant of the well right here. And it multiplies well force by time multiplier. So that's all. That's we just call this. Wow, I really don't remember this code. Probably should have commented it better. But these videos are the comments. Maybe I should have watched the video. Okay. So I created a rib renderer for the cell. So that last animation you saw was, I think, generated in Maya. Maybe? Yeah, I think so. But, you know, to get away from Maya, like I said as a goal, I created, is it render.ml? No. Render script. Oh, it's render script, I bet. Yeah, here we go. Okay, so cool. Render script is a program that reads my cell files, you know, the descriptions of where all the cells are, their positions and sizes, and then creates a rib file, which is a RenderMan render file for those cells by just creating, well, it sets this, well, this scale is to change coordinate systems. But regardless, down here, sphere, it creates spheres for the cells. So it scales it, translates its position. This scale actually is for handedness. This switches our handedness because Maya and RenderMan have opposite handedness. This brings it to a reasonable scale. Okay, so let me show you what that produces. And also, so our render script is wired into our make file now. Render script is here. And where's the rule for turning a cell file? No, I don't remember. Sorry. Anyway, so here are the spheres. You can see the render errors from Pixie here. Let's render that. Let's watch that a couple times. So very much like the last one, except now we're rendering real spheres in the Pixie renderer, the RenderMan Pixie renderer, so that you can do it. You can do it all yourself on your side if you don't want to use commercial software. And we'll be using this again in a bit. So what do I do for run 36 now? Lots of files. Create cell to map generator. Okay, so yeah, lots of files here. So just like we used to have these cell files, right, which are descriptions of the state of the system at every frame. Now we seem to have height files and render files. What is this? And we have this new MapGen. What MapGen does is it reads the cell file and then generates a map for the cells. And it's very similar to what RenderScript was just doing, but it does it by hand in C code so that we can control it better. Let me show you what I'm talking about here by open cells dot what. Let's get a late frame number. 122 dot height dot tiff. Okay. So this is what it produces. You can see we're getting away from the individual, the cells being very spherical, and we're getting to a more organic sort of look here. So how does MapGen do this? It does it very easily. It reads in the cell file, and then what does it do? And then so it reads in the cell file here, and then it loops over all the cells, and for every cell it draws this little gray image where that cell is. And what is that gray image? It's some kind of funky formula that I guess made sense to me a year ago. Yeah, I need to create these videos much closer to the time I write the code, or I need to comment the code. Oh, see? Simple metaball. So I'm doing a simple sort of metaball computation here. But the point is, now that I have these images like this, you notice it's named height. I'm going to use these as height maps or displacement maps. And let me show you what that looks like. Open cells.0.122.render.tiff. Yeah, there we go. Okay, so check it out. When you use that as a height map, this is the shape you get. And how do I use that as a height map? I load it into a shader somewhere. Am I still using the Stalag shader for this? No. Oh, celldisplace.sl is the name of the shader for that. Ah, yes. Ah, yes. So we look up into that texture map, that height map. If the height is greater than this little small number, then oh, and then we add some noise in here too. We add a noise function. So a little bit of randomness at different strengths and sizes. This is like fractional Brownian motion noise here. So yeah, so a lot of this bumpiness is coming from the shader. It's not coming from the cells themselves, but the basic shape is coming from the cells. So let's look at the animation of this. That is not the animation of this. That's the animation from last time. Let's remove that. I need to clean up, man. Do I have any other animations here? No. Okay, so let's open it into our image viewer, and then we'll just poor man render it. So here you go. Okay, so that's kind of cool. I don't know about that looking like skin, but maybe it looks like mold growing. Maybe. Yeah. Still needs a lot more work. What did I do in run 37? Give the cells pits. So I in the center, so in that height map file I generated, let me open one of these again too. I changed the height map this time. What I opened 122 last time. .height.tiff. Let's see if we can see it here. Yeah, so here's that same height map as before, but you'll notice I have cut holes in it for the cells, because I'm going for this funky look, and this will maybe help me create it. The code to do that is in the MapGen, of course, and it's very simple. when we're generating that height field, we now have a little bit of code that cuts out a pit. This is the pits. Cells.move. Let's see what that looks like. Okay, so that's a little creepier. Yeah, I'll let the animation run longer. Watch that again. So it's creepier, but and it's interesting. You know, there's a lot of neat properties to notice here. But still, we need more. Add lighting, point light source, add surface shader with specular, turn off rough displacement. So that noise, the noise I've been talking about, I guess I turn that off. Turn pits into bumps, and instead of having little pits, now I have the bumps. I reverse the direction of the bumps. So what do I mean by surface shader? Did I do it in cell displace? No way. No. I added a. I didn't write my own shader for this. I used, what did I use? I used one of Pixie's shaders. Plastic. I used their plastic shader. So let's look at the movie for this one. Okay, so specular highlights are the the bright white patches where the surface catches the light, and yeah, again the pits, they're not pits anymore. They're bumps. They bump out, and that's interesting. That's interesting. We're getting something. I think that's closer to my whatever my grand scheme is. I like the black oily look. Yeah, but we need more work. We need more work. 39. Create custom surface shader. Add environment maps. Remove bumps and smooth. Smooth. I wonder what smooth means. Okay, so for this one, I actually wrote my own custom shader. Like last time I used the plastic shader, right? But now we've got this cell surface shader, which is pretty simple. We just do a reflection. It's just reflective, and we look into an environment map. What is that environment map? It looks like this. Well, what? What is that? Yeah. This is an environment map that I got for free, for non-commercial use only. So nobody use this. Nobody make any money off of this. Otherwise, you have to email Dan Meyer. So what does an environment map do? Let's see. Cell.move. Where are my movies? No movies in here. Okay, well, render.tiff. We'll do the poor man's animation again. So like last time we had the shiny thing going on as it caught the light. Now we're going to have some serious shine going on because I'm using I'm ray tracing reflections. It's not actually totally ray traced. So early on we see, and I removed the that rough bumpy, that rough noise, because now I've decided I'm going for this oily thing. So, you can't really see the environment map here because it's just so wackadoodle. But this is the sky, and this is the greenery around on the ground. You can't see the houses or anything, but that's pretty cool, huh? I think at this point I was really pleased with myself. I vaguely recall that. The cells seem to have a problem. They don't look like they merge in right away. They look very dotty. I don't want them to look that dotty. But the reflection map's cool. We're starting to get a much better look. And we got it right away just by using a reflection map. Now, if I recall, I did a million things here. Yeah. So here, I added the bumps back in because I want the cells to be distinguishable. Don't add the bumps together. Take the max of the bumps. Oh, so when the bumps would overlap in the other renderings, I don't need to draw it. When the bumps would overlap, I would add them together. But now I'm just taking the max so that they don't create little I don't want them to grow together like that additively. And then yellow red, what's that about? Let's see. Well, I don't want to spoil the climax here. What I want to show you is that it's very simple because I did this all procedurally. Remember, procedural is good. It was really easy for me to drop to switch out the Q. Right, super easy to switch out the Q for other letters, and so that's cool. Well, let me just show you the animation. Yeah, so there you go. Let's loop that and watch it a few more times. So what I've done is on those bumps, remember, I have modified the reflective function to filter the color from yellow to red based on the shape of the bump. So here, this I will draw because it's interesting. So say we have, this is our Q again. Say this is a bump of our Q, right? Up here, where the surface is completely flat and the normal points up, it's yellow. And over here, as it points to the side, so this is yellow, and over here, this is goes to red. And it's a gradient from there to there, and that's all. Yeah, there are things about this I like and things about this I don't like. But I think this is pretty much right around where I stopped. I think I did a couple more versions, but this is pretty much it. I think I might need to change the font. I chose that font. Yeah, no, I want a better font. I chose the font because it was kind of didn't have a lot of variation in thickness, but maybe I should do that. And the cells are looking very spherical, which is not natural. I mean, it's kind of cool looking. I was going for something like this. Looks very, I don't know, alligator skinny where the cells are, like down in. It's very annoying that it does that. I hate that you do that. Here, how about, if I make you bigger, will you stop getting in the middle of my letters? Yeah. So, yeah, maybe let me make this bigger so that. Yeah, there are a few interesting things going on here. And then the one last thing I did, which I don't think I have an animation of. Oh, but I have a, oh yeah, maybe I do. Q.move. What do we got here? Is this it? Yeah. Oh, yeah. Oh, yeah, this is much better. This is closer to what I wanted. Yeah. Okay, so cool. I didn't do the whole QLab version of this. I just did the Q. But a couple things here. I got rid of the at the beginning of the video of the last one, the goo started out gray, and I didn't like that. I like the the completely opaque oil business. And then I also changed the shape of these guys. You'll notice they're not spheres anymore. They're sort of spheres that when they get close to each other they get flattened out. Let's see. And you're wondering, well, how the hell did he do that? It's really easy. You just, in addition to computing that bump, what you do is you watch to see. To compute the bump, you have to know. Well, you don't have to know. But what I do figure out is which cell is, when I'm computing a particular pixel, I figure out which cell is closest to me, right? Then I also figure out which cell is second closest to me. And when the distance between those two is almost equal, I flatten out. I create this little flat space in between them. This is a trick kind of known as, if you've taken my shaders class, which you probably haven't, but you should, cellular noise. Cellular noise, so you can see it's going on here. That's that trick. You can Google for that. Or you can take my shaders class. How's that? Yeah. Okay. Let's watch that one more time. I should have made the whole QLab out of like this. I wonder why I didn't. Did I do that? Did I do renderings for the other letters? Oh yeah, I've got. Oh yeah. Open a dot move. Oh, I just need to stitch them together. I didn't load them into my editor. Yeah, this pleases me. This is, this isn't anywhere close to where I want to go, but this is a nice stopping point. And that's why I stopped a year ago and got distracted with other things. Mainly teaching my classes. Okay, so that's all. Like I have said in previous videos, all of these files are available to you on the interweb. Wait, do I have a QLab? .move? No, that's the old one. No, that's the new one. What an idiot. So I did totally generate this one. Is that... No, that's the old one. These guys are merging together. I didn't generate a new one. Let's look at that README. Yeah, that README. Use cellular noise technique to keep cells from merging. Create flat space between. I wonder if I changed anything else. Well, whatever. So I'll put all these files on the net, and you can download them, and maybe this is useful to you in some way. Thank you for listening. Take care. Bye.